Okay, I think we're good to get started. Most people are here by now. So yeah, this week we're going to be basically running our own machine learning model and train it on like the MNIST dataset to basically recognize like handwritten digits. I guess before we even get into the lesson, Trevor's not going to be here this week. I think he had like a meeting for his like AP exam or something. So yeah, he'll be here next week, but not this week. And also, like, if my internet cuts out or like my mic starts doing something weird in the middle of the lesson, please let me know. I've been having issues with that lately. Yeah. So I guess ready to get started. This week basically we're gonna be doing everything in Google Colab. So if you want to like follow along and type along as I do, you can click the link I put in the challenge room chat. It's like the student copy of this week's code. And then you can click File and save a copy in Drive to make a copy of this entire like notebook, and you can type along. If you just want to watch, that's okay as well. Yeah, and if you have any questions, I'll be watching the challenge room chat. So I guess let's get started. So first thing is just some stuff before we get into any of the code. First thing we're going to do is talk about tensors. So this week we'll be creating a neural network model in PyTorch and training it on the MNIST dataset. But before we get started with the code, there are some things we should cover. So first of all, PyTorch and other ML libraries like TensorFlow handle data in objects called tensors. Tensors are basically multi-dimensional arrays. So for example, if you have a Python list like this, where it's 1, 2, and 2, 3, there's two arrays in one bigger array, it's a two-dimensional array, right? And that's also like a 2D tensor. So you can create tensors using the torch.tensor function, which returns a tensor object, and you can pass both Python lists and Numpy arrays into the torch.tensor function, and it will convert either of these objects into a PyTorch tensor object. So for example, I have this code here. I think I gave you guys all of like the sample code just for this section because yeah. So we import the torch library, we create this variable x, and we basically instantiate it with the torch.tensor function, and we're passing in just a two-dimensional array with the values 1, 2, 3, and 2, 3, 4. So you can see how that's a 2D array, right, with just two subarrays. And if we run this code, I have to connect to it. Yep. Take it a second, and then we get this output. So it's a tensor object, and it basically just contains our Python list that you have to pass tensor objects when you're working with PyTorch like models or functions. They won't really accept Python lists. And then we can get the shape of a tensor object using the shape field. So if we print this, we get this torch.size23 object. So the first, so the shape of x is 2, 3, which makes sense since it's a 2 by 3 tensor, right? So we have two dimensions here, and then like I guess I should say two like arrays here, and then three values in the last dimension, right? So, and then yeah, you can tell like the actual like overall dimension of a tensor by getting the length. So because there's two values here, we know it's a two-dimensional tensor. Yeah, here's an example of a 3D tensor. So if I run this code instead, you'll see that it'll give this size object here with three values. And because it has three values, we know it's a 3D tensor. And then yeah, I instantiated this using this like weird list object here, which is like a bunch of nested arrays. It can get kind of tricky to wrap your head around tensors when like the shape is complicated like this. But I think if you like really stare at it and kind of like look at how the brackets are positioned and stuff, they can start to make sense. So in this case, we have like two subarrays, which each contain three subarrays, which contain two values. So it's a 3D tensor with these values in it. And tensors also have a data type as well. So when you create a tensor, you can specify which data type you want it to contain. For example, so here's the same, it's a tensor with the same values, but it has different data types. So we can make it a float32, a float64, aka a double data type, or an int32 data type. I think by default, PyTorch will either make it an integer data type or a float data type, depending on what you provide it. So in this case, because I just provided integers, I think it would by default do this. But if you gave it floating point numbers, like Python floats, it would instead do this. So if you really want it to be one specific data type, you should provide it, but yeah. Yeah, it is kind of like a matrix. It's pretty much the same thing, except I think a matrix has to be 2D. I'm not sure. But I think the tensor is like the generalization of it. But yeah, it definitely is like a matrix for sure. And then, yeah, one final thing about tensors we'll talk about is the dot view method. So sometimes in machine learning, you want to change the shape of the data in a specific way, but like you want to keep the data the same, just like you want it to have like a literal like different shape, right? Like in like the tensor sense, like it's just in a different, like it's organized differently basically. So for example, you might have a 2D image, but your model only takes a 1D input, which is actually what happens in our example. So we'll see this later on. In this case, you can use the dot view method to like convert it to a 1D input. So for example, you have this 2D input here. These are just random values. 1, 2, 3, 2, 3, 4. If you, let's actually run this code here. So if you just print the tensor, right, it's still 2D. And then here, just for fun, I just made it 3 by 2 instead of 2 by 3. So it's still 2D, just it's organized differently. And then in this case, I made it all flat. So I basically put everything on one row. And this -1 here, obviously it doesn't make sense. Like you can't have the size -1. But when you call .view, PyTorch interprets -1 as like, it basically tells it to like guess what the length is based on the number of data points you have. Remember that like your resulting tensor has to have the same number of elements as the original tensor. So basically, if you have like one -1 value, TensorFlow can calculate, or not TensorFlow, sorry, PyTorch can calculate the like the amount of values that should be in that dimension, and it can basically just set it. So yeah, -1 basically tells like PyTorch just put everything else into that row. So it's just like a nifty little trick. So you don't have to compute that by hand, like whatever that value actually is. I think in this case it's 6, but it might be different in other cases. Yeah. So if you want more info, there's like a bunch of different like methods on it. Yeah, you can like cast it to other data types. You can like, yeah, there's lots of different things. You can read about it at this link here. It's just like the reference. I won't like go into it for the sake of time, but yeah. And then one other thing we'll talk about is softmax. So in classification tasks, we often want the output of our model to give probabilities or confidences in each class. For example, if our model outputs 1, 5, and 2 as scores for 3 classes, it's hard to work with this output, right? Like, what does 5 mean? What does 1 mean? What does 2 mean? But instead, if it outputs something like this, like 0.0171, 9362.466, we can easily interpret this number as like the model's confidence in that class, or like a probability. So in this example, the model is 93.62% confident that the input corresponds to the second class. And in order to like get this to this, we basically use something called the softmax function. So softmax is an activation function which scales the values in such a way that they end up representing a probability distribution. So the sum of the outputs is 1. And yeah, that's really nice. So here's an example of this. So we have some array 1, 3, 2, 5, 2. Pretend this is an output of some model. And yeah, in this case, you actually have to set the data type because by default, PyTorch will make this integers, and then softmax will complain because it doesn't know how to work on integers. So you have to make it float 32. And so yeah, we create this softmax function, like we instantiate the class, and then we can call it on this raw output to normalize basically these scores and make them nice. So in this case, you can see not very confident in the first class. It's like kind of not really confident in the second class, not really confident in the third class, super confident in the fourth class, and not really confident in the last class. So that makes it really nice, just to like look at the output and get like a meaningful result out of your model. So we don't use the softmax function while training at all, actually. Instead, we feed the raw outputs to this special loss function called the cross-entropy loss. Cross-entropy loss is a good loss function for classification tasks. For the sake of time, we won't go into depth into it, but you can look it up. basically, yeah, whenever you're doing classification, unless it's like something really weird, most of the time you'll probably be using this. It basically just combines like, I think, log softmax and NLL loss into one layer. Like, don't worry if you don't know what those are, but it basically, yeah, it just does the activation and the loss function for you, and it packages it into one thing. So that's pretty cool. Yeah, that's pretty much it for the background. I guess from here on, I'll kind of show you guys how the whole PyTorch setup works. So the first thing we'll look into is data parsing, and you can click these little arrows, by the way, to like expand a section. So the first thing we'll do is we'll import all of our libraries. So let me scroll down here. So you can just click in the code box, and you can select everything and just delete it. And you can start typing in Python code. So in this case, we want to import PyTorch. So you do that by typing import torch. And then we also want to import some sub-packages from PyTorch. In this case, we want to import the NN package. NN contains like all the neural network stuff. Yeah, that we'll be using in this project. Next, we want to import torch vision. And we want to import from torch vision, we want to import data sets and transforms. And this will basically help us parse our data set and download it, which is what we're going to be doing in this chapter. And we also want to import matplotlib. So you do that by typing, it's like a little weird, you have to do, yeah, it actually shows up as a recommendation. You type in matplotlib.pyplot, and then typically you want to rename that to something more friendly, like PLT. And we also want to import Numpy. So import Numpy as NP. And this is all like the libraries we'll be using for this like example. So we typically just put those at the top, just so we don't have to worry about it. Yep, cool. So now that we have those down, let's talk about some of the transformations that we're going to be applying on the dataset. So basically, when we download the dataset, which I'll show you later, it's like the function you use to get it basically gives you all of the images as like Python images, like the Python image library like objects, but we want them to be in tensors, right? And we might also just want to do some other pre-processing on the data. So in any case, like we have to do some sort of like transformations on it, right? So I'll kind of show you how that's done here. So basically, we'll just make some variable called the transform, which will like hold these transformations. And if you want to do just one, you can just set it equal to like some transform function. But in this case, we want to do multiple, so I'll just make it a transforms.compose class. And this takes in an array, basically, of transformations. So in this case, I'll apply the following transformations. The first thing we'll do is convert it to a tensor. So to do that, you basically, there's this toTensor object in the transforms class, and it basically, you just specify it in this compose, and it will take the Python image and convert it to a tensor. And then on top of that, we want to normalize the, losing my voice, geez. We want to normalize the image as well. So this code is actually right down here. It's a little bit funky. You might be wondering how I got these numbers, and I'll just explain that in a second, but yeah, don't worry about this for now. I'll explain it in a second. And then after that, so after we've converted it to a tensor, the image, and we've normalized the image, we might also want to do some other stuff to it. In this case, as an example, we'll just apply a random rotation. So you can do that by doing transforms.random rotation 15. And then the 15 is just like the angle that, the maximum angle that PyTorch will randomly rotate each image. So like it might rotate it anywhere from minus 15 degrees to plus 15 degrees, like clockwise or counterclockwise. And there are other things you can do as well. I don't know if you guys have heard, but I think there was like an article a while ago that was like getting attention where like a lot of like computer vision algorithms would get like fooled by noise. Like computer scientists would just add like a little bit of noise to an image, and the model would be like completely thrown off, even though like you really can't even see the image, like a human eye couldn't. So some people like add like random things like blur or noise to their images before they train. So like the model hopefully learns not to get confused by the noise. In this case, we'll just do like a random rotation, which can like help it find patterns. But yeah, of course, there are other things you can do. You can look up like the reference for the transforms and try applying your own. And cool. So now let's explain what that normalize thingy does. So this transforms out normalizes the image using this formula here. So it takes the image, like the actual like pixel values, and it subtracts the mean, which is this value here, and it divides it by the standard deviation, which is this value here. And yeah, we set this mean and standard deviation to be these values respectively. If you're wondering how I got these values, basically the actual MNIST dataset, like if you go on the site, it will like tell you what these values are. If your dataset doesn't tell you what the values are, you can compute them manually by going through the dataset, adding all the pixel values, and like dividing by the total, get the mean, and then using the standard deviation formula. Yeah, in this case, the MNIST people are nice, and they gave it to us. Oops, I need to edit that. And then if your image has multiple channels, you need to set the mean and standard deviation for each channel. So if you see when I called this, the mean is actually inside an array. That's because you have to specify a value for each channel. In this case, the images from the MNIST dataset only have one channel. They're what's called grayscale images. Like you might know how regular images have a red channel, a green channel, and a blue channel. In this case, the MNIST dataset only has like a white or black channel, like a gray channel, I guess. So there's only one value, so we only have to set one mean and one standard deviation. Done. And then we will pass this entire like composition of transforms into a function later to apply it to our dataset. So yeah, any questions with that? I know I kind of went through that. Mean and standard deviation of what? Is it the number of pixel? No, it's the mean and standard deviation of like the actual pixel values. So basically, like your pictures, they're composed of like color. Yeah, they're composed of like a grayscale color, and we basically want to like normalize that so that the mean is 0 and the standard deviation is 1 over all the values, because it turns out that that machine learning models train better when the mean is 0 and the standard deviation is 1. So that's why we subtract the mean color and divide by the standard deviation in the color to normalize all our images so that the mean is 0 and the standard deviation is 1. Okay, yeah, I know this is a little bit weird. I think actually if you saw like last week, I don't know if you guys caught this, but in the model I provided to you guys, the data has a mean that's like offset from 0 quite a bit. And so it actually takes like a bunch of epochs. Like I think I had it like 10,000 in order for the model to like move, like the bias to move all the way down to where it's supposed to be. So yeah, it really helps a lot if your data set is properly like normalized so that the mean is 0 and the standard deviation is 1. Otherwise, you'll take a penalty in training time as your model has to like do more work basically to converge. Cool. Okay, so let's move on to downloading the actual dataset. So let's okay. So I mentioned earlier that the Torch Vision library offers some like convenience functions for downloading the dataset. Like you don't actually have to like download all like the images by hand. Oh, okay. Sorry, Michelle said something. Someone from Yearbook asked me to share a picture of the club members, so ask your VC if they're okay with taking a screenshot of everyone's profile pics. Okay, so someone from the Yearbook asked us to take a picture of the club members. Are you guys okay if I take like a screenshot of everyone's profile pics? I don't know, like type in like a yes in like the chat if you're okay. Cool. I mean, I don't know if we're gonna be able to get everyone to spam yes in here. You can turn your camera on if you want your face to be in the Yearbook. I might have to stop sharing actually just to see everyone. Oh, I don't. Okay. I don't think I can even fit everyone into one screen. Jeez, a lot of people here. Let me take a quick screenshot here. The computer's lagging like crazy because of the stream. Okay, I'll just paste that in the chat. You can turn on your camera if you want, but it's fine. I don't even have mine on, so let me ask Michelle if that's me. Oh, sorry, what was that? Oh, true, yeah. I forgot that Discord has that limit. Yep. Turn our cameras on because there are more than 25 people. Okay, I'll just keep moving on. I think that should be fine. Okay, so now for downloading the dataset, yeah. So Torch Vision offers some convenience functions, so you don't have to like download the images manually and then like read them like using Python and stuff. So I'll kind of show you how that's done. So basically, the first thing we do is we instantiate a datasets.MNIST class. So I'll kind of show you that here. So basically, just type this MNIST should be datasets.MNIST. And then this takes a bunch of parameters. So the first parameter it takes is like the location of where you want to save the dataset. So in this case, we can just save it in a folder called datasets. And then there's some other options. So the first option is whether or not you want to download it. So we do want to download it in this case. So we just set download equals true. And then this will tell Torch Vision to actually download it and save it in that folder. And then there's another option called train. Train. So basically, if you set this to true, it will download the training dataset. If you set it to false, it will download the testing dataset. So because this is our training dataset, we just set it to true. So it'll grab the training version for us. And then there's also a transform option. And this is where the transformation we created earlier applies. You can actually specify the transformation we defined earlier, and it will apply this to all of the images in the dataset. So yeah, that's pretty much how you grab it. And then now to actually it turns out that you can't just feed this into your model. You have to create something called the data loader to actually load all of the data in this dataset. And so we'll just call it train loader. And we instantiate a torch sorry, I should have imported this earlier so I don't have to type all this out. Data loader class, and then this loads the data from this dataset, and it takes some parameters as well. So the first thing we give it is our actual training set object, and then we have to set the batch size. So I think I kind of mentioned this last meeting, but basically when you have big data sets, you don't want to compute your backpropagation on the entire data set at once or just on one value. You want to do it in batches, which are just the right size for your specs. So in this case, we're training on CPU. Something like 64 is good, but maybe on a GPU, you could probably actually turn that up quite a bit because they're more powerful. But in this case, we won't worry about that. We're just doing simple CPU training. So yeah, we'll set it to 64. And there's another option that we'll use called shuffle, and we want to set this to true. In order to basically shuffle the data set when it gets downloaded. Yeah, I don't think it matters too much, but it might help. I'm not too sure, to be honest, but I think it's probably good to add more randomness into the data set things. Cool. And now we want to download the testing data set. So you can basically just copy paste the code over for testing. And then the only difference is we want to set train to false. Remember how I said that if you set this to false, it will give you the testing version? So, yep, set it to false, gives you the testing version, and then same thing. Now we just want to rename the variables to test instead of train, so that you don't clash. Yes, and then set that to that. And then we can also increase the batch size on our testing dataset because we're not backpropagating the gradients, or and we're not storing the gradients at all. So we can just set this to something bigger, 256. And boom, now we have a loader for both the training dataset and the testing dataset. And we'll use this later on to actually get the images from the dataset. And then yeah, remember that these are all, they're now parsed and nice, and because we defined this transform up here. And yeah, that's pretty much it for the dataset then. There is some others. Actually, there's some quick stuff we should do. So I guess once you've done all this, you also want to like actually test that your data set is, that your like loader is performing the way it should be, and that your data set is like good. Can you zoom out so we can see? Sorry, one sec. Don't think I can. Let me try. I don't know if somebody can figure out how to zoom out and take like a picture of like more of the students. That'd be cool, thank you. But I couldn't figure out the zoom. Okay, and then so yeah, now it's like a good idea to test that your code works so far. So we do that by defining this. Well, we do that by basically showing like a batch of images. But in order to do that, we have to define a function to actually show the image, because you can't just call like print like test loader like 0 or something, right? And just like print the first image. You have to like do a bunch of stuff because they're in this weird format that we made up here. So we'll define a function, show image, and it will take in like an image data. And then the first thing we want to do is unnormalize our image. So remember how we normalized it up here by like subtracting the mean dividing by the standard deviation? We basically want to undo this, and we do this by basically first multiplying by the standard deviation. So we set that to be what, 0.3081, and then we want to re-add our mean, so that's 0.1307. And this will basically undo this normalization and give us the original pixel values. Cool. And then the next thing we want to do is convert our image to a Numpy array, because matplotlib, which we'll be using to actually show the picture, doesn't like tensors, it likes Numpy arrays. So we'll convert that to a Numpy array like so. You can just call image.numpy, and this will set the Numpy image variable to be a Numpy array with the image data. And then we can do plt.imshow. imshow basically like takes the matplotlib like plot, and it pastes like an image in there, and then we'll pass it. I'll write it out first so I can explain this a bit easier. So basically, we'll take our Numpy image, and we basically just want to permute the rows. So it turns out when we actually call this image, I'll show you in a second, but we'll use like a special function to like paste the images together. And when we do that, like the image for some reason like scrambles like the rows in like a specific way. So we want to basically undo that so that's in the right format for matplotlib plotted. And then yeah, you basically just do that by calling this Numpy Transpose. And this is like the order of the rows. So we basically want to put the second row first, the last row second, and the first row to the last. For some reason it brings like the color channel to the front. I don't know why. So yeah, this fixes that, and it shows up the right way. And then we basically just show our plot. And then now you can see like the image when you call this function. Again, I'll be providing the teacher reference as well. So if any of this, if you don't get this down, or I think I might have some comments in there as well, you can consult that as well. But yeah, this is basically how you show an image. I know it's a bit convoluted. That's how you show an image with this dataset format. And now, now let's actually get an image from our dataset or a batch of images and show it. So the first thing we want to do is convert the train loader into an iterator. So we do that like this. Again, with the way PyTorch classes are set up, you can't just access it. It's you have to do some funky stuff to get it. So in this case, we have to use the Python function iter to convert it to an iterator, and then we can get a batch of images by doing this. We can set our batch of images, and our labels is data iter.next. So we get the next value in the iterator, aka the first value. And then now we can actually call show image on this. So we can do show image. And now you could show just the first image, but just so you guys can get a better vision of what the size of a batch, there's this function called torchvision.utils.make_grid. And you can actually pass it your batch of images, and it will basically just make them into a grid. And then we can just pass that into our show image function, and that will make everything into a grid. And then I also had some code to like yeah, I'll just leave that out. I had some code to like show the labels as well, but it's kind of convoluted actually. And it might be cool. Here, I'll paste it in. Here's some code to like show the labels as well. Oops, I didn't mean to paste that. It basically just prints like each of 8 labels on one line and makes like a grid. I'll show you in a second. You don't worry about that if you don't want to. Now let's actually run some of this code because I think I've been forgetting to do that. Cool. Now let's run this and see what the output is. So you'll see it downloads the dataset, and then boom, there we go. So here's the output of our actual code. And so you can see these are the actual images in the dataset. This is what one batch looks like. So it's an 8x8 grid because there's 64 values, right? And here are the labels. So you can see the first image is labeled with a 6, 9, blah, blah. They're all labeled correctly, hopefully. And this is what we actually feed in our model. Just obviously the actual pixel values that are normalized, can't just like feed it like an image like this. And so yeah, that means we successfully downloaded our data set and we have it parsed and everything. So that means we're good to go for training. If there are any questions, nope. Awesome. So yeah, that's pretty good. Again, if you have any questions about this code after, like, feel free to text me or like or even Trevor as well. I think Trevor like wrote some of this code, and we can like help you out. And I'll be giving you as a teacher copy as well because I know it's like a bunch to go through. Okay. So now that we've done all that, let's move on to actually training. This is the exciting part. No more boring data science. So the first thing we're going to do is define our model. So we do this by, well, there's actually 2 different ways you can do this. The way you'll see in most tutorials is like they actually define like a full class that inherits from nn.module, and they define like they like override a bunch of the functions. In this case, we're going to keep it simple, and we're just going to use something called the nn.sequential class. And what sequential basically does is it lets you, it's like compose. It lets you bring together a bunch of layers into like one object really easily without like having to define like your own class to do it. So I'll kind of show you. So you basically just pass it each of your layers. So the first layer will type in, it's our input layer. It's a linear layer that takes in 728 inputs and outputs 128. So yeah, linear layer is just your regular dense neural network layer. They just call it linear for some reason. Well, I guess it is linear, but yep. And then after that, we'll use the ReLU activation. I think Trevor talked about this last meeting, but ReLUs, if you add ReLUs between your layers, like it helps speed up training. Then we'll add a hidden layer, and then dot linear, which takes 128 inputs and takes and outputs 64 outputs. One thing, by the way, actually, this value here is the actual input to like your linear layer. This is important. This is actually dependent on your data set. So in this case, we have 64. What do you call it? Like our batch size is 64, right? And then I think each image is like 64 by 64 or something like that. Like this depends on like your image size. It's like this one you can't mess around with. Like later on I tell you guys to mess around with stuff, but you can mess around with these values here. Just make sure that the output of one linear layer is the same as the input of the other one, or else it will complain. And then yeah, let's add another ReLU layer, and we'll add our output layer, which which goes from our 64 neurons and outputs 10. So again, the output is also important, right? Each number can only take 10 values, like 0 through 9. So this has to be 10 as well. Like you can't change that. And then yes, now you can see now we have all these layers. The sequential model basically groups them together into one model. And yeah, so you don't have to define a class to do that. But a lot of the other like tutorials, you'll end up defining a class, which can tidy up your code. I guess I'll show you why later on, but yeah, for now we'll just use this because it's simpler. Are there any questions? Sweet. Nice. Okay. So yeah, now that we defined our model, again, let's go through it quickly. Just 3 linear layers, like regular neural network layers, with some ReLU activation functions in between. And these help speed up the training of your neural network. Like, it's been like proven. There's been like some papers. We won't go into explaining that because yeah. And then we have no activation function on the output because the cross entropy loss basically does that for us. So nice. So we can run that and boom, all is good. Next thing we'll do is define our loss function and our optimizer. So we'll just say loss function equals nn.cross entropy loss. There we go. And we instantiate that. And then we'll set our optimizer into torch.optim.atom. So I'm using the atom optimizer. You can also replace atom with SGD, which is what we learned about last class. But I think atom generally like trains a bit faster, so people typically use it. But both will work. They're created the same way. So the first parameter is model.parameters. These optimizers need to know like what your model shape is. So you have to pass it the parameters from your model. And then we also have to specify a learning rate. I think there is a default one, but you typically want to tune it for your application. So in this case, we set it to like 7 times 10 to the negative 4. I found that this value works. Like I said last time, there's like a bit of trial and error involved with getting that right. And yeah, now we have our loss function and our optimizer. The next thing we'll do, now we get into a bit of like some of the more tricky code. So we have to define a function to evaluate our model on the actual training dataset. So we do this by defining a function called validate. And it will take some inputs. It'll take our model as an input. It'll take the test loader as an input. And it will take our loss function as an input. And we want it to basically spit out what the loss is, like the total loss over our training data, over our testing data set, and the accuracy as well, right? The accuracy is a important metric to consider as well. So I'll kind of show you how to do that. The first thing we want to do is to set our model into evaluation mode. I think this time it doesn't really matter, but if you end up adding like dropout layers and stuff to your model, it's important to turn those off when you're evaluating, right? You don't want to like drop outputs when you're evaluating. So that's what this does here. It basically turns off like all those funky layers that mess with your outputs. And then we want to type in with torch.noGrad. And then what this does here is it executes this code block like that's going to follow without recording the gradients, which speeds up things a little bit. Because remember this, like when we're validating, we don't care about the gradients because we're not going to be backpropagating at all. We just want to see what like the loss is. So with torch.noGrad, we'll set our total loss equal to 0 and our accuracy equal to 0. And then we'll iterate over our test loader. So for images and labels in test loader, where images is again a batch of images and labels is a label for each image. We will, first thing we'll do actually before we feed it into the model is we'll use that .view function we talked about earlier. So yeah, because the images are 2D, but our linear layer takes in a 1D input, right? We want to just resize this like so. Shape. There we go. So what this does is it basically keeps the batch size the exact same. Remember, we don't want to mess with the batch size, but everything after that, it basically just makes it into one long array, right? So it just it's a 2D array where the first dimension is the number of batches, and the second dimension is just all of the pixels in the image in one array. Cool. And now we're ready to feed that into our model. So we'll just do that. We'll say outputs equals model, and we'll just call it on this the formatted image batches, and this will give us a variable called outputs with like our model's predictions, and then we'll increment the total loss by the output of the loss function, right? So we'll take the loss function, we'll compute it over the outputs and the labels. The labels, by the way, I don't know if I mentioned this, but yeah, labels is basically like the truth, right? This is like Y truth, and this is like Y prediction. Remember like the formulas from last class. And then in order to actually get, it's like weird in PyTorch, for some reason this like the loss functions return like a tensor with one value inside. It's like a zero-dimensional tensor with just like one number inside. I don't know why they do that, but in order to actually get the number out of it, you have to type .item, and this will give you a regular number you can work with. So then, yeah, now we can actually add it to our total loss. And then now we want to compute the accuracy. So we'll just define a variable called equality equals, and then we'll just type this out real quick and explain it. So outputs.argmax. So basically what this does here is, so the first thing it does is it computes, oh I mistyped that, the argmax. The argmax over each output from the network. So what does this do? So if our network, I haven't done it yet. If our network outputs 10 probabilities, right, argmax basically gives us the index of the largest probability. And so this is important, right, because this index is basically what the prediction of our model is, right? If our model is like 90% confident that the output is at index like 5, like if it outputs 0.9 at index 5, that means it's like 90% confident that the output is 5, right? So yeah, I don't know if I explained that right. I'll show you in a second, but argmax basically gives you the index of the largest value. And then if you set dim equals 1, like remember, we don't want to compute it over the batches. We want to compute it like over the outputs. So if you do dim equals 0, that's the batch dimension. So it's the wrong one. You have to set it over dim equals 1 because that's the actual like output dimension. This is what I mean when I start saying that dimensions can get a little bit convoluted. Usually what you probably want to do is like print the output shape and just like mentally read through it and make sure that you understand how the dimensions work. But yeah, we're not doing that this time. And then you can check when there's this equality sign here. This actually compares it element-wise. So you basically get a tensor of booleans, whether each element lines up. So that'll tell you if the label equals the output, right? Like the output prediction. And then we basically set this to some variable called equality. And then in order to actually like add to our accuracy number, we basically just do accuracy plus equals. Yeah, this part is a little tricky as well. What you want to do is just compute the average, right? And then get the item. So you compute the average over all of your like booleans, right? Like a true is a 1 and a false is a 0. So if everything is like spot on accurate, you'll get an accuracy score of 1, otherwise a 0, right? You want to compute the average over all of this. But it turns out if you just do this, there's integer division problems. So you first have to cast it to a float tensor, float tensor, and yeah, that fixes that issue. Cool. And then yeah, I encourage you guys to like add print statements in here where you're like trying to understand the code after, just to make sure you get everything, because I know like it's easy for me to like say this, but like understanding it is like different. So make sure you like actually like look through it. Cool. And then let's once we're done with that, we basically just return the total loss, the average of the total loss. We want to divide it by the length of the test loader, and we also want to return the accuracy. So we'll return the accuracy divided by the test loader. Oops, by the length of the test loader. And we want to multiply it by 100 to get a percentage. Let me see if there's any questions there. We'll let you know a little bit. Oh, okay. So that's pretty much our validation function there. It's like the actual training function has like a very similar shape as you might imagine. Just the only difference is that we're actually going to be backpropagating. I'll show you guys that in a second, but first let's test our validation function in our model. So yeah, let's just type that up. So we'll just say our untrained. Oh, let's actually run this first so that we have it cached. Okay, untrained model metrics, and the first thing we'll do is print our testing loss. So let's actually call the validation function to get that first. Test loss, test accuracy equals validate, model, test loader, loss function. And so now we'll get the test loss and accuracy of our untrained model over the testing data set and using our loss function. And let's print that out. So test loss. And then we'll also print our accuracy. So print, oops, testing accuracy, test accuracy. And yeah, that should be good. And then, yeah, we'll just leave it at that for now. I had some other code in there, but I don't want to bog you guys too much and we're running out of time. So let's run that and see what we get. I think it actually should take a second. So this is basically running over all of the images in the test loader. Oh, that was pretty fast. And we get the following data. So we have this test loss and it's like huge. It's like 2.3. That doesn't really make sense, but it's just like a really big number. And our testing accuracy is basically 7%, right? And yeah, that's like terrible because think about it. If you're just like randomly guessing what the number is, there's like a 1 in 10 chance you get it right. So it's like, technically it's doing worse than randomness, but in reality it's like pretty much random. So yeah, so obviously we have some training to do on this model. It's no good right now. So now we'll define our main training loop. We're finally here. So let's set the number of epochs first. We'll just set that to like 24. That's what I found is like, it's pretty good. And then for epoch in range epochs. So we'll just run this over 24 epochs. We'll reset our running loss to 0. Again, this code should look familiar because we like just wrote it up here basically, just like some slight tweaks. This time we'll set our model to the training mode. And we'll iterate over the images and labels in the train loader. And now is where the code starts getting a little bit different. The first thing we want to do is 0 the gradients in the optimizer. Basically think about this as like prepping your optimizer for this batch. You have to do this at the start of every batch so that your optimizer is like resetted basically. Yeah, it's just like a PyTorch thing. And then again, we want to resize our images. So actually we can just copy paste this code because it's the exact same up here. Want to resize the images so that it's just basically like one long array with numbers so that our model will accept it. And then boom, we do the same thing. We just run that through our model, get some outputs, and then we get the loss by calling the loss function with our outputs and the actual truth, and then we backward this loss. So we basically backpropagate it, and then we call optimizer.step to actually update the weights of our model. And then finally, we also want to update our running loss. Oops, that should be plus equals loss value. And then we like increment our running loss with whatever the loss value is. And that's actually like enough to train. Now I'll just add like some print statements to like. Oh, I guess also we should run like our validation function as well to get like our test loss and our test accuracy. This is the exact same as we had up here. Cool. Now I'm just going to add a bunch of print statements. Yeah, I'll just paste these in. This is enough to train, but yep, I'll just paste these in to save some time. So again, we print the epoch number, we print the training loss, the test loss, and the testing accuracy. So our training loss is again the average of the running loss over the entire length of the train loader. So it's basically just the average. I mean, you don't have to take the average, but it doesn't really make sense because if you have like different lengths of your data set, you'll get like weird values that you can't compare. So people take the average of it. And then, yeah, so this will actually train, but now we also want to save our model, right? Oh, make sure you're muted. Okay. And then we also want to train our model. So basically, save our model. So basically, if you think about it, it doesn't actually make sense to save the model each epoch, because like hypothetically, what happens if like just like one epoch your model just like goes crazy and it like the actual testing loss gets worse? Then like it would overwrite like a better model you had saved from the epoch before. So what you actually want to do is you want to define a variable called your best test. Oops, there should not be a space. Best test loss. And this will basically keep track of your best testing loss, and you only want to save whenever this improves, right? So if one epoch is better than the best test loss of all the other epochs, then you want to save, right? You don't want to save otherwise, or else you'll be like losing progress. So to start, we'll set this to like infinity, because we have nothing left, so we want to like save it on like the first epoch. But we'll update this if we find something better. So again, if the test loss is lower than the best test loss, then we want to save our model. So print saving model, and we'll call torch.save. This is used to save our model data, and to get the actual like model like weights, you call this save dict function. It's like it's like a dictionary with all of like your model parameters, and that's what PyTorch uses to like load and save your model. And then we like you have to add a path as well. In this case, we'll just call it model checkpoint.pth, and this will save it right in the same directory, but you could specify a different path if you wanted to. And let's not forget to update this value. Cool. And then otherwise, just say that the testing loss did not improve. Nice. And then we could just add a new line. Let's run this. All goes well. Hopefully there are no mistakes. I think actually it takes it a little bit to run, so maybe I'll move on to the next step. We're shutting on CPU, so it's like a little bit slow, but yeah, a few epochs should come through by the time we're done. Anyway, and the final step is after you've actually trained your model, you want to also load and evaluate it. So actually, we're getting pretty close to 3. So maybe I'll just actually no, it's pretty simple. To load your model, you basically just write this. So, oops, looks like there is a mistake. Sequential object has no attributes saved it. What? That's weird. Oh, it's state dict, sorry. Yo, what's up? Yo, nice. Oh, I think we're just... Oh, okay. Nice. Yeah, that should be model.stateDict, not saveDict. I don't know why I put that there. There we go. And then yeah, if you call this here model.loadStateDict and then torch.load the same path you specified up here, you can actually load your weights back in, and you can actually evaluate it. So now instead of running this, I've already like pre-ran this training loop. Let me see if you guys can see that. Oops. Oh yeah, okay. So I've already ran this training loop for like 6 epochs. You can see how like the accuracy improves, the test loss goes down, and then I just interrupted it because it was running for a while. If you let it run, I think around, I mentioned it later, but around 16 epochs, it gets a 99.1% accuracy, plus or minus a little bit because it's random. So yeah, this model is good enough to get over 99% accuracy, which is pretty good. And then if you load the actual weights and you set it to the evaluation mode, we can actually basically compute it on an image and then show the upper probabilities. So in this case, here's the image that was randomly selected. It's like a 5, but it's like really, like, yeah, it's obviously handwritten. And yeah, the label is a 5, so we're hopefully our model will output 5. And here are the output probabilities. This is pretty amazing. It's like, it's basically 1, which is, it's actually impossible, but like with floating point error, like it actually ends up being 1. And 0, 1, 2, 3, 4, 5, yeah. So the output is a 5, and it's 100% confident that it's a 5, and that is what the image is. So yeah, you basically just learn how to train MNIST with like 99.1+% accuracy. So congratulations, you made it through. I guess yeah, let's just cover some final notes. So yeah, this is good enough to get over 99% accuracy in 16 epochs. Here are some ideas for improving the model. There's like some quick tweaks you can make. You can try adding some more hidden layers. You can modify the width of the layers, but remember you have to like update 2 values when you do that, because like the input of one layer has to match the output from the previous layer. You can try adding dropout layers or other forms of regularization like L1, L2, but they're a little bit tricky. Probably have to do some research. You can look into convolutional layers if you want a head start on next week's lesson. You can probably get a pretty high accuracy with convolutional layers. Like they offer some significant improvements over regular dense layers in computer vision. Yeah, you can look into batch normalization, LR scheduling. This is actually like if you want something like pretty simple to improve this significantly. I know. I think the learning rate after like 16 epochs is too high for it to train. So if you could somehow lower that a little bit, like after 16 epochs, it would probably continue to train a little bit. So LR scheduling would help with that, learning rate scheduling. And you can also look into other model evaluation metrics, like something called a confusion matrix or an Ock-Rock curve. There's lots of them. And yep. So training and validation can also be sped up using a GPU or a TPU. Yeah, I don't know. I think this dataset is too small to be honest, but you can. Colab offers free K80 GPUs to mess around with, and you can do that with these settings. If you pay a fee, you can get access to Colab Pro, which gives you access to a more powerful GPU. I think it's like the V100. But you can do a lot with just the K80. Oops. I recommend looking up some tutorials though if you do end up using a GPU with PyTorch, because you have to like change some stuff in the code. And yeah, I think that's pretty much it. I'll send you guys this copy as well as the video so you can review. But there's lots of great tutorials. Convolutional layers are pretty cool actually, if you are interested in looking into those. I think I was added. Let me take a look at that. Yep, I'll be posting the finished version as well because I know I ran out of time and I had to speed through it at the end. Yep, if there are any questions, I'll just answer those quickly right now. Otherwise, you're good to go for this meeting. Okay, yeah, I don't see anything, so good job, guys. You made it through. Let me share this with you guys now.